climate changes, as well as levels of pollution in remote areas. He chaired the science committee of EPICA, co-chaired IPICS, and currently he holds an ERC for studying the past stability of Western Antarctic ice sheet, and is going to present processes affecting dissolved and particulate aerosol compounds. So, Eric, you should be allowed to share your screen and start your presentation.
Okay, thank you very much. Does that look okay? I think so. Okay, good. So I'm going to be hopefully pretty brief here today. I'm really just a warm-up act for the other speakers. I think we felt when we were putting this together that the two other talks might look as though they were technical things that not all ice core people might be interested in, but actually they're really important. And so I said that I would give a little talk explaining why we're worried about what happens to material after it gets trapped in the ice sheet. And then the other two speakers will present new ideas that help us understand that. So there are lots of impurities we measure in ice cores, and I've just listed a few of them here, the ones that are in what I call the impurity phase as opposed to the gas phase. I've included the cosmogenic isotopes there, I won't list them out. And we measure them for all kinds of reasons, for dating, layer counting, okay, not at old ice core sites, which we're talking about mainly today, but for volcanism, for understanding sources and transports, and also for understanding artifacts in the gas phase. And last time we had the talk from Jochen Schmidt about nitrous oxide and the importance of reactions on dust that might be creating nitrous oxide as an artifact. I think generally when we're looking at the chemistry in ice cores, we mentally assume three things, or well, we probably assume lots of things, but there are three things that I want to mention that we assume. The first is that what we see in the shallow ice reflects what was in the atmosphere somehow. And that's generally true, and we study air-snow transfer to understand that. But there are some near-surface post-depositional effects, which are particularly acute at low accumulation sites, and they dominate what we observe at places like Dome C in terms of nitrate and MSA, and they affect cosmogenic 36 chlorine. We're not going to be talking about those today, but I think that Joel Savarino is giving a talk about that in a future seminar. Then a second assumption we generally make is that the ice, we can date the ice and assuming it's in chronological order. And we know that's not true, particularly for places like Nîmes, and especially when we get near the base of the ice sheet. Pretty much every time we've got near the base of the ice sheet, we find some kind of disturbance or folding. So that's a problem for all our analyses. It's nothing special to do with aerosol compounds. And again, we're not going to be talking about it today. But then the third assumption that we tend to make is that once the material is buried in the ice, once it's got to maybe 3 or 4 meters down, it just stays unchanged. It doesn't move anywhere, it doesn't diffuse, it doesn't react. And unfortunately, that turns out also not to be the case. So that's what today's session is really about. So there are a number of processes that certainly worry me that are going to concern us when we come to looking at the oldest ice core, especially the beyond Epica oldest ice core in our case, but other people looking at old ice or ice that's near the base of the ice sheet. The first one is this phenomenon that's, I'll go through each of them in turn in a minute. The first one is this phenomenon of aggregating of dust. A second one is diffusion, which, because the material will have been a long time at warm temperatures, is particularly acute because it's warm near the base. And then the third one is the possibility of what's called anomalous diffusion, which is what Felix will talk about. So just to go through each of those in turn, the dust aggregation observed firstly in Dome C showed that there was an anomalous large mode observed from 2,900 meters down. It appears possible to split these large particles that you can see there by ultrasonic treatment. And it was originally suggested there might be a chemical mechanism going on involving iron. And I think we'll hear a lot more about that from Giovanni later. Well, why does that matter? Well, firstly, because dust itself is an important parameter and we tend to use dust numbers. So if lots of particles are aggregating, we get it wrong. The second one is whether there are chemical reactions, because if there are chemical reactions, they may be taking things out of the soluble phase that we generally measure in CFA and putting them into the insoluble part or vice versa. therefore meaning what we're seeing near the base might not be the same as we would see it near the surface. And thirdly, things like those aggregates you saw will be inhomogeneous, causing something misleading with anything attached to them. And beryllium-10 is the clear example we've seen, where many of you will know that in Dome C, a large part of, a very important part of the dating was observing a beryllium-10 peak associated with the magnetic reversal at 780,000 years, which you can see down. I'll just change my pointer, which you can see here on the bottom figure, which is very clear. It's very obvious. I'm quite convinced that's the Brunias-Matuyama boundary. But the raw data was actually the data at the top with all these spikes in it. And we think that that was probably caused by the fact that beryllium is stuck on dust particles and the dust particles were aggregating. So as you're drilling through a particular section or taking a very thin section from the ice core, sometimes you're hitting an aggregate, sometimes you're not, and it's giving you all these spikes. So the way that this was treated by Reisbeck et al. Was to take medians, and that seemed to work. But was that justified? I think we need to know more about that. So that's one example where dust is important for things other than just dust. Then the second issue is diffusion. We're not really going to talk much about just plain diffusion today, but just to say it does happen. We know that volcanoes are typically 2 or 3 years wide. That's to say the material falls out of the stratosphere in typically 2 or 3 years, and that's seen near the surface, as you see in the top diagram. But by the time you get to 100,000 years, what's obviously a volcano appears to be 20 or 30 years wide. So there's clearly some diffusion occurred. It might be through grain boundaries. We'll maybe hear a little bit about that. We've estimated the effective diffusivity in the Holocene section, and we're actually doing some work at the moment on other sections. But it's just to mention that's another thing that we're worried about. And the reason why that's a problem is what I said before, that the old ice has been warm for a long time. It's been near the bed. It's not quite as warm, hopefully, at Little Dome C as it was at EDC, at Dome C itself. But still, it's probably been within a few degrees of the melting point for several 100,000 years. So that's a worry, and raises questions about what scale of detail we can hope for in the oldest ice. And then finally, there was this question of anomalous diffusion, which was raised by Alan Rempel back about 20 years ago. It was a very clever paper and a very clever idea. I never quite believed it, but I couldn't ever put my finger on why I didn't quite believe it. So the idea behind it, and I'm sure Felix will talk more about this, is that if the impurities are actually liquids at grain boundaries, then what happens is that the solute concentration in the grain boundaries is determined by the temperature of the ice. And so you essentially do have a small concentration gradient in the ice as you go deeper. And the effect of it is to advect the impurities relative to the ice, so that you actually would end up with the impurities related to a particular age of ice being deeper than the ice that they belong in. I guess the reason why I never quite bought it is because I knew from the data that we didn't really seem to see it. At Dome C, sodium should be displaced from the other signals by several meters, according to this theory, and yet it quite clearly isn't, as you see down here, where you've got the isotope signal and the sodium signal, and it's not very high resolution, but there's clearly not been movement by several meters. So what we'll hear about today, that's really just an introduction as to why we're worried about these things. That any of these, advection would clearly put things at the wrong time. Diffusion would make them impossible to see. The dust clumping will give us some strange results and might actually degrade our cosmogenic dating, for example. So the two talks we're going to hear today, I think Felix has reassessed this so-called Rempel effect and described another aspect of it, which I think, we'll see what he says, I think it turns out to reassure us a little bit that we don't have to worry about it quite as much as we thought, although only because there's something even slightly more complicated going on that we hadn't thought about. And Giovanni's going to look at more detail at what happens chemically to dust as it gets deep and old in the ice sheet, so addressing the first question I raised. So with that, I think I've done my job of trying to explain why this is important, and I'll pass back to the organisers and unshare my screen.
Thank you, Eric. Does anyone have any question for Eric for this very short but complete introduction? Looks like no one has any question. But I think we will have a lot for the two other subjects which are more in details.